Um, okay, so I don't know if I'm being heard right now, so I guess there's a lot of background noise, but I don't know if I'm being heard, but I'm just gonna make this the intro for the stream. This is my first stream, and I hope, like, the first of many more, hopefully. So today we'll be doing the Jan 2022 unused paper for Unit 5 Physics, and yeah, I hope this will be a very fruitful lock-in session. So yeah, I might also add like lo-fi background music to my next streams. This is just test, because the account that I want to stream on doesn't like requires me to have 24 hours. To told me I need to wait 24 hours to be able to stream. So yeah, um, I'll be doing the paper in this booklet here that's been provided to me by my school, and you guys will hopefully be able to see this PDF that I have open with the very same questions, and at the end we'll mark all of them. I'll try and be vocal about what I'm thinking and my thought process through the questions. Um, so yeah, I hope you guys find this useful, and I think we'll start. So time of start is 13:50 East African time, at on the day of 20th April 2026. Fine. Okay, I hope I don't end up like not speaking for like majority of this. um, I don't know a lot of physics, so I'll try my best to get things right rather than just skipping them or assuming the right answer. So yeah, the first question is, for the fusion of hydrogen nuclei to take place in a star, the temperature in the core must be very high. Which of the following is a reason why the core must have very high temperature? Um, so there's usually only one answer for this question, out of the four. The reason why hydrogen nuclei need to have a high temperature is because temperature is just a measure of kinetic energy, and they would require to have a very high kinetic energy to be able to overcome the repulsion, uh, electrostatic repulsion between the nuclei, because both nuclei are positively charged, or the nuclei are positively charged, so they need to have enough kinetic energy to come close together. So that is B. Right. Okay, question 2. The average density of the planet Mercury is 3 times that the average density of Callisto, okay, which I believe is a moon. Yeah, okay, it's one of the moons of Jupiter. I believe Callisto is a Galilean moon, but I don't know, I could be wrong. Mercury and Callisto have approximately the same diameter. At the surface of Callisto, G is 1.2 newtons per kilogram. Which of the following is the value of G at the surface of Mercury? Fine. Okay. Right. So G is the gravitational, I don't know what it's called. Uh, the gravitational whatever like thing. Oh god, this is not off to a great start, but yeah, okay, fine. I think, again, I think newtons per kilogram, 3 times greater than the average density of Callisto. Okay, it's 3 times greater average density, so I guess it has 3 times greater uh, mass for the given volume, given that it has the same diameter. So so the mass of Mercury is 3 times the mass of Callisto. Okay. So I would like to assume that it should exhibit 3 times the gravitational force onto another massive body. So its G should be 3 times that of Callisto, right? And 3 times 1.2 is 3.6. Now this could be, I could be horribly wrong, so I don't know. I don't know. I mean, I should know this. I would choose C, so I don't know if that's right. But then I don't know why I feel like it's D. Why do I feel like that? I have no clue. So yeah, I guess this shows why I need to lock in and why I'm doing these streams. I am not actually looking at chat. There's no one in chat. I think. I don't think there's anyone in chat. There's no one watching the stream either, so I guess this mistake is a secret between me and whoever watches the stream later on. So yeah, I don't know what the answer is. Let's think about it. I have all the formulas here, right? We can look at what G is, right? The gravitational field strength, that's what G is. Okay, and we can go to, oh my days, I just dropped the paper. No, there we go, found it. Fine. So we know that, do we know? We can just look. Gravitational force is this, right? No. Okay, fine. I'm just gonna stop overthinking it and say that it's C. Let's say, haha. Okay. In the decay of cobalt 60 to nickel 60, the mass decreases from 59.934 atomic mass units to 59.931 atomic mass units. Which of the following expressions gives the energy in joules released in this decay? Which of the following gives the energy in joules? So, of course, you would have to convert the difference. So it's the difference of the two. So 59.934 minus 59.931, the difference of that, times 1 atomic mass unit is, let me just confirm, should be 1.66 times 10 power 27 kilograms. 27? Is it 27 or negative 27? Should be negative 27. Let me just make sure that's right. Speed run all the way to the end. Where are the constants? It is negative 27. Thank God. I mean, there was no reason for me to check that, but because it's all here, there's the stuff here, so I could just use that, but I don't know, man. Okay, negative 27, and that's the mass in kilograms, and then because of our good friend Einstein, delta E is equals to delta M C squared. I mean, not because of him. I mean, it was always equations. I understand that you could confuse it for A, because instead of using atomic mass unit, you use the conversion of electron volts to joules instead. But yeah, no, that's not the one. So I don't know what I'm doing. B. Fine. Question 4. Just some of these wrong. I hope I don't. I like MCQs. Okay. The amplitude of an oscillating system is observed to increase over time. Which of the following types of oscillation is the system demonstrating? Give me a minute. Let me just check something. Hello? Okay, it's the same. So it's using the I don't know what mic my recording's using. I hope it's not too loud or too not loud or too much like background noise, because I have my fan on because it's like hot here. Also because I'm wearing a hoodie because I'm a bit mentally challenged. But other than that, I hope the stream's enjoyable. Oh. Gufran's in the chat. Hello. Yay. Um, Gufu man, I feel dumb. Oh wow, poor. Okay, so it's just said that my stream quality is like really bad. Wow. But that's fine. Yay. Let's see. Um, okay. This has motivated me more. Thank you. Thank you for letting me know that there's no background noise. I'll continue on to question 4, I guess. Okay, the amplitude of an oscillating system is observed to increase over time. Which of the following types of oscillation is the system demonstrating? Fine. So the amplitude is increasing over time, so it's not damped or natural. I don't know what a free oscillation is. Probably an undamped, undriven oscillation. So I'm just gonna say it's D because it seems right. Fine. Question 5. An experiment carried out to investigate the absorption of gamma radiation by lead. An experiment is carried out to investigate the absorption of gamma radiation by lead. The count rate R from the gamma radiation is measured with different thicknesses of lead between the source and the detector. As 1.5 centimeters used, count rate is reduced from R to R by 2. Which of the following gives the count rate when the lead of thickness 4.5 centimeters is used? Fine. So when the thickness is 1.5, the count rate is halved. So I would like to assume that when it's 3, it's halved again, right? So half of R. So it's R by 4. Okay, so at 4.5, it's half of half of half. So it's R by 8. I don't know, man. I'm saying it's D. Next, question 6. A mass suspended from a spring set into vertical oscillation of amplitude 4 centimeters. The frequency of the oscillation is 1.6 Hz. Which of the following expressions gives the maximum velocity of the mass in centimeters per second? I did not pay attention. Wait, 4 centimeters and has a frequency of 1.6 Hertz. Maximum velocity. Okay, so again, trusty formula sheet because I don't remember formulas. We know that next paper, where is it here? Oh god, it's a mess. Have I lost my paper? Just, yeah, no, it has everything I need. Okay, V is A omega sine omega t, negative A omega sine omega t. So knowing that velocity would be when sine omega t is 1, so we can just remove the sine, so it's negative A omega. Negative A omega is the maximum velocity. So given that the maximum amplitude is 4 centimeters, and we want in centimeters per second, okay, omega is 2 pi f, right? So 2 pi times 1.6, so that's, what's that, whatever, that one. And A is 4 centimeters, right? So times 4, so 4 times 1.6 times 2, so 4 times 2, 8 pi times 1.6, so it's C. Question 6, C. Nice. Okay, question 7. An astronomer is using a standard candle method to determine the distance of a nearby galaxy. Which of the following quantities must the astronomer have values for in order to determine this distance? Which of the following quantities must an astronomer have in... Okay, so they're using a standard candle, so they need to know the luminosity of the standard candle, the intensity of radiation emitted by the standard intensity of radiation from the standard candle at the point where he wants to measure that one. So A, I believe. Luminos, no, no, yeah, it's A. Fine. A mass is hung from a spring and set into vertical oscillation. The oscillation is damped. Which of the following is not a correct statement? Okay, the mass is hung, no, 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 it's damped. It's not a correct statement. The amplitude of oscillation decreases over time. I think that's correct for a damped oscillation. Frequency of oscillation decreases over time. I don't think so. But maybe, I don't know, let's see. Maximum kinetic energy of the mass decreases. I think that makes sense as well, because the energy is being moved away, so its maximum kinetic energy would decrease. The total energy of the system decreases over time. Okay, like F is like that, and like it slowly whatever's. I don't think the frequency of the oscillation would decrease. Would it? Because let's assume it's a spring, or a pendulum. Yeah, a spring that's oscillating. Its time period is 2 pi root. It's a spring. Yeah. What was it? M over K. Just make sure. Just make sure. Don't embarrass yourself on stream. Where is this? Is this even in the? It should be. It should be. I remember seeing this somewhere. If it's not in this paper, that would be very funny. Right, it's not in the paper. It's not in this one. I could have sworn. Okay, I'm just gonna assume it's L over G, so it should be M over K, right? Yeah, I think it's M over K, right? Either way, this is not changing, this is not changing, this is not changing, so of course it can't be that. Yeah, so frequency does not change. Yeah, and I don't know if the rest are right or wrong or scenario based. I don't know, man. Okay, the Hertzsprung-Russell diagrams, X, Y, and Z show the stages in evolution of a star cluster. Which of the following sequences of diagrams represent how the star cluster evolves over time? So, fine. So diagram X, there's literally no main sequence stars. I think there's a few red giants, and then I don't know what the rest of those are. Probably red supergiants and red giants as well. Okay, and a few white dwarfs. Diagram Y is just a normal whatever, which I believe would be the initial stage. So I'm saying diagram Y is first. And then it should go to Z and then to X, but X just looks off. I don't know why. But yeah, X is probably last. Z is the in-between stage where the high luminosity, high temperature, big stars start dying out, and not dying out, so leave the main sequence and go to, yeah, so Y, Z, X. Y, Z, X. Part question, that one. B. Okay, question 10. Okay. A graph shows, I just kicked my phone. Okay, let me just check chat quickly. It's D. What question is this for? I'm lost. Kufu, are you still there? What question? Okay, wait, don't tell me, I'll figure it out. Don't for 4. Oh shit. Oh yeah, okay, it's D. Yeah, I got it. Thank you. Okay. Question 10. The graph shows how the binding energy per nucleon depends upon nucleon number for a range of naturally occurring nuclides, nucleids, whatever, nuclides. Binding energy per nucleon in MeV against nucleon number. Which of the following can be deduced from the graph? The binding energy for tin is greater than it is for uranium-238. Yes, but binding energy for tin is no, maybe, I don't know, because it depends on the binding energy per nucleon and the nucleon number. So we'll get back to that later. Nucleus of oxygen is more stable than a nucleus of tin. I don't know. More stable. I mean, okay. The higher your binding energy per nucleus, the lower the chances of it decaying. And I would like to say that oxygen has a lower binding energy per nucleon than tin, so technically oxygen would be less stable. So I don't know, but we can't really determine that because gas, solid, nuclear stability, I don't know. Fusion of hydrogen with a proton to form helium will increase energy. With a proton to form helium, it won't release energy, will it? Yes, it will release energy. Okay, I guess, because the binding energy per nucleon increases. Fine. Uranium-238 can release energy by spontaneous fission. I don't know. What do you want me to deduce? Which of the following can be deduced? So the binding energy for tin is greater than that for uranium. You can deduce that from the graph, but I don't know if that's right. So we have 120 times tin is about 8.2. I don't know. So it comes to 984, and 238 times 7.5. I don't know. No, yeah, 7.5. Yeah, so it's not. So A is wrong. So it's not A. No. Okay. Nucleus of oxygen is more stable than that of tin. Again, I don't know, right? That's 8. It's 8 against 8.2, right? So technically tin is more stable than oxygen, so I guess B is wrong. The fusion of that that is true, it will release energy. And I also know that it's true that uranium-238 can undergo spontaneous fission to release energy. It still does it release? Yeah, it releases energy. So I think D feels more correct than C, because C just feels wrong, right? Because I don't think it would want to fuse with just a proton. I mean, I don't know what I'm saying. I'm just yapping. So I'm gonna say it's D, and then call it a day. I'm not calling it a day yet. Right. So now we're at a crossroads. I can either mark this first. No, you know what? I'll finish the entire paper. Let's move on to the big questions. The big questions. A balloon was filled with air. Okay. Until it was an approximate sphere of radius 18.5 centimeters. The pressure exerted by the air in the balloon was 1.04 times 10 power 5 pascals, and the temperature was 22.5 degrees Celsius. Okay, number of air molecules. Okay, so we know the radius. Okay, underline radius, not diameter, radius. And we're supposed to find this. Okay, we're supposed to find the volume because we're going to be using PV is equals to NKT to find N, right? K is the constant, gas constant. Is it the, I don't know what name it is. What's the name of that constant? Where is it? Boltzmann constant, not the gas constant. That's 8.31. Okay, Boltzmann constant, and temperature in Kelvin, and pressure, and then volume. Volume should be in meters. So the radius in meters is 0.185 meters. So the volume in meters squared, sorry, cubed, is 4 over 3 pi r cubed. That is the volume in meters. So this should give us the volume, which I will calculate. 4 by 3 pi times 185 power 3 is 0.0265 meters cubed. Did I? Yeah, okay, I did that right. Fine. So we have that and that. So N is PV over KT. So N is pressure, which is 1.04 times 10 power 5 times volume, which is 0.0265 divided by K, which is 1.38 times, just make sure, 38? Yes, times 10, x to my 8 times 10 power negative 23. Just making sure. Yeah. I should wear my glasses. My glasses. Okay. I don't know what I'm doing. Okay, 23 times temperature, which is 273 plus 22.5, which will be 295.5. So the N is that 1.04. Just making sure. Any chats? Okay, fine. Anyone in chats? I haven't checked this here. I have 3 views. Oh my god. Uh-oh. Is my Wi-Fi being weird? Okay, fine. My Wi-Fi is just very, very, very not good today. I mean, it's never good, but today specifically. So the number of molecules is 6.76 times 10 power 23 molecules, rounded to 3 significant figures. 6 times 10 power 23, sorry, 23. There. Nice. Question 12. The wavelength of a line in the spectrum of light. What does this look like? Okay, fine. Looks fine. Oh, this is what you guys are seeing. Are you guys? I don't even think you can see much. You're just listening to me talking. So yeah. Either way, 6.76 times 10 power 23 was the answer of the previous question. So in this question, the wavelength of a line in the spectrum of light from a distant galaxy was measured to be 436.6 Newton meters. The same line is measured in the lab and has a wavelength of 434.1 Newton meters. Okay, calculate the distance to the galaxy. Fine. So we can find the Z. I don't know what Z stands for, but using delta wavelength over the wavelength in lab, and that is equivalent to velocity of the spectrum producing galaxy divided by the speed of light. So of course the delta is 438.6 minus 434.1 divided by the lab one was 434.1. Okay, so redshift of course equals to V over 3 times 10 power 8. And then so we know that V is this value times C, which I'm just going to calculate because I don't want to write it down because we don't have space in this small booklet, small puny useless booklet. I don't like the school booklets. I should have bought one from Gufu, but I didn't because I don't know. I should have. Well, okay, it's moving at a speed of 3.11 times 10 power 6 meters per second. And you want to find the distance. We have been given the Hubble's constant, so we know that, again, just confirm. No harm in confirming. You'd rather confirm and spend 20 seconds than be wrong and fail. So V is equals to H naught D. Right? So we have that. We have that. We can find D. D is V over H naught, such that D is that divided, okay, that's the answer, divided by H naught, which is 2.3 times 10 power negative 18, right, per seconds. So it's 1.35 times 10 power 24 meters away. Nice. 3 marks. We have secured ourselves a lot of marks out of 90. Not a lot, but I don't know what I'm doing. How long have we been streaming? 35 minutes. 35 minutes and I've done absolutely nothing. Is that locked? Did someone try open the door? It's 2:20 right now. No one's gonna try open the door. Okay, I thought it was like time for my sister to come home. We have time. Okay, a student was asked to explain what happens when radioactive decay occurs in a sample of uranium. Okay, the student gave the following response. Radioactive particles are emitted from the uranium over time, or uranium, okay. Over time, the rate of decay decreases as the uranium becomes more stable. Okay, the mass of the sample decreases by 50% in a time that is equal to the half-life of the uranium sample. Okay. Radioactive particles are emitted from uranium. I don't think that's right, because